Okay, let's start part 5 where we try to introduce the cumulative line spectrum map. And then we're going to apply it to several pianos. To get started, let's take a look at a hypothetical 3-note piano. C1, G1, and A2. Each has 3 or more harmonics. Here are the pictures of the waves of these 3 notes. Here's the sound of each. Okay, now here's the line spectrum of the C1 note and also the G1 and the A2. You can see where the peaks are located. C1, for example, has got 4 partials. The second partial is the strongest. Over here I've got the cumulative line spectrum of these same notes, which corresponds to the line spectrum. And I'm seeing, for example, that I've got the most strength at the third partial on the G1, and I've got the most strength at the second partial on the C1. Now let's construct the cumulative line spectrum map, and it's just the same thing as these 3 cumulative line spectra, except it's all on one plot. And I'm plotting the frequency along this axis, just like I'm plotting the frequency along that axis. I'm plotting the percent of accumulated signal power along that axis, just like over here. But I'm also plotting against the note number. Here's C1, G1, and A2. So it's the same information that I have on these 3 spectra. It's just on one plot. Now let's look at the cumulative line spectrum map of the Canabi grand piano. Okay, we see here quite a busy plot. I'm plotting the keys along here, 1 to 88 or A0 to C8. Over here I'm plotting the frequency. And over here I'm plotting the percent accumulated power. The difference between this graph and the previous one is that I'm plotting the frequencies logarithmically. That's because the fundamental frequency as a function of the key number is geometric. So when I plot this scale on logarithmic units, I can plot the fundamental frequency in red here as a straight line. So we start out here at 27.5 for A0 and go all the way up to 4186 for the C8. We've got several sections marked off here, demarked by the blue lines. For example, from 1 to 8 keys is the bass area that is single string wound. From 9 to 16 is the double string wound area. Here is the triple string wound. That's the end of the bass section. Over here is the treble section, which are triple strings. Here's the treble. And then here's the upper treble, where there's no dampers. So we see, for example, down here at the low numbered keys, that there is no appreciable power at the fundamental, or the first partial. And in fact, there's nothing at the second partial. It's not until the third partial that we start to see a small amount of power showing up. And then, for example, the very lowest key, A0, there's just a little bit at the third partial, and not even, it's the fourth partial before you see a real step. As you go up in frequency, you can see that more and more there is a migration towards having more power at the first partial. You can still see the steps here as we are dealing with the first, between the first and the second harmonic along here, so forth. Okay. Oh, and then over here at the far right, at the highest notes, we see a situation where there's a lot of power appearing at frequencies below the fundamental. For example, up here at the highest key, C8, there's only about 25% of the power is actually at the fundamental, and all the rest of it occurs down here at lower frequencies. This is the so-called hammer knock. Okay, let's look at the lowest 30 keys of the Kanabi. So this is the same data that was plotted on the previous plot, except I'm only looking at 1 through 30 now. And this shows, for example, this red line is the first harmonic, or the fundamental. The magenta line is the second, black is the third, red is the fourth. And this is a little bit clearer picture. It shows where these keys start to show strength at the lower frequencies. For example, it isn't until about the 20s, maybe the 19th key here, that you start to see a significant amount of power at the first partial. And then here's the second partial, third, and fourth. Let's look at the autocorrelation map for the lowest 4 notes on the Kanabi. Now this is simply a plot of the autocorrelation, plotting lag time versus autocorrelation, -1 to +1, 0 out to 60 milliseconds. And of course at 0 lag time, the autocorrelation is at 1 on all 4 of these keys. We're looking for the highest peak. First of all, you see there's a lot of peaks going on here, so it's a little bit muddy as to what the true pitch might be as according to the autocorrelation. For A0, we do have the top peak here at the red post, which is plotted at the fundamental frequency of 27.5 hertz. Peak occurs again, same place for the A0 sharp at the fundamental. It's a little bit off here for B0, and then you see it's right in the center, a little dip, the peak here for the C1. So according to the autocorrelation, the pitch of each of these notes, if you will agree that it comes at the highest peak, is pretty close to the fundamental frequency. So this particular graph suggests that the line spectrum can give you a picture of where the power is distributed in the frequency domain at the various partials. The autocorrelation takes all of that distribution into account and tries to locate a peak that would point to where the pitch is in the frequency domain. Now let's take a look at the area where there's this hammer knock. Okay, here, this plot is the plot taken from the first plot. It's just the 65 to 88 numbered keys. And here's our power at frequencies below the fundamental. And I used the microphone to collect this data. Now here's the same area of numbers, the key numbers that is, 65 to 88, but now I used a transducer attached to the soundboard. So it is not going to hear the noise associated with the action movement, and you see there's no appreciable hammer knock here. Now the Yamaha console has a similar map. We have same areas demarcated by the blue line. For example, down here from 1 to 13 are single wound strings. 14 to 30 are double wound. Then we have 3 triple strings that are wound. Then we get into the triple strings that are single-stranded for the tenor. Here's the treble and the upper treble. See, there's quite a bit of hammer knock. Might even say there's a little bit more than there was for the Kanabi. But there's a similar characteristic of having, for example, the lowest notes, lowest keys, having no power, appreciable power at the fundamental or the second or third partial. Now we also can look at other pianos. There's 4 other ones that I've looked at. They're loading right now. Here they come. Okay, here's the Yamaha P120, which is a digital piano. You can see there's on this particular piano there appears to be a lot less hammer knock, but that was because I used the earphones output of the piano when I collected this data. So it didn't, by definition, it wouldn't hear the action noise. This area down here is a little bit different for the Yamaha. This digital piano is supposedly based on samples from the Yamaha, I think it's the CF3S. Here's the Model D up at St. Paul's in Ithaca. Quite a bit, you can see quite a bit of hammer knock up here. Similar behavior down here. Here's the Busendorfer. Similar structure to the other pianos. Hammer knock. The lack of power at the lowest keys at the lowest partials. And then here's the Schimmel with a similar structure to it. Okay, now just for laughs, let's take a look at a hypothetical piano. I constructed this cumulative line spectrum map to make it look smooth. So there are no abrupt transitions here. But it does have the characteristic of the other pianos that at the lowest keys, there's not much power at these low partials. How does it sound? Well, actually, before we do that, let's compare it to the Canavi that I showed you before. Okay, here's this theoretical piano, and I put piano in quotes up here, and here's the Canavi. You see, it has, in some sense, similar characteristics. Okay, let's listen to these 2 pianos. Okay. There's the Canavi. Okay, that compares the 2 pianos. And then finally we'll show where those notes came from. That was Louis Armstrong, of course, on his famous introduction to West End blues.